please allow me to introduce Matt, who's going to be speaking about reverse engineering flash memory for fun and benefit. Thank you.
Yeah, sorry about the late start actually. So this talk is about reverse engineering the flash memories. So it's not the Adobe Flash actually. So I worked on a lot of Adobe Flash vulnerabilities, but this one is about the physical flash memory. So the flash memories are used everywhere these days. For example, the USB sticks you have, probably it's using flash memories. And the flash memory is really small, smaller than a quarter. And all the embedded devices, something like Dropcam or smart appliances and cameras and phones, they are using some form of NAND flash memories. And the target device that I'm showing today is actually about the POS device you can see everywhere these days. If you live in US, probably you saw this device. So this device is from Verifone, so one of the major manufacturer of the payment device. And this device is really expensive actually, around maybe $800 or $1,000. But from eBay, you can buy some aftermarket device. It's like just $30. And you just open it up. The truth is that actually I'm not a hardware hacking guy. Actually, this device is the first device I ever seriously hacked or reverse engineered. So I just look into the inside, and I have no idea what other parts are doing, but some things are clear, right? So here, the Samsung CPU, it's ARM CPU, and the other two chips are Samsung DRAMs, and the other one is NAND flash memory. So you can just look up the model number from the internet, and you can easily find data sheet. And if you look up the data sheet, you can find the specification. On the right side, the pins are for data I/O, 8-bit data I/O, and left side is for data control. And the first step, when you are using NAND flash memory reverse engineering method, is actually doing desoldering. So you might wonder there might be other way, easier way, to not performing any kind of desoldering or serious hardware stuff. So I thought of this. So someone are actually selling this from some market. So this 360 clip is actually for hacking Xbox 360. So the way how they are doing is actually retrieve the firmware from Xbox 360 and just modify it and just flash it again. So somehow this one works for Xbox 360, but it didn't work for me probably because it is supplying some current to the board, PCB board, and actually it's waking up other parts, and it looks like it's interfering with our operation. So it didn't work for me. And this one is actually really expensive, like $50 or something, just clip. And the other option is desoldering the chip using ChipQuick. And I tried this on other types of chips, but kind of this one makes the chips really messy, and the PCB board is kind of like filled with all those remaining solder fluid or whatever. So I didn't really like it, but other guys actually use this a lot, I guess, but I didn't like this option actually. So the last option I found is just straightforward, just using hot air and just melt the solder and just take out the chips. And to do that, actually, you need one solder, SMT rework station. You can find it from Amazon or other places. And this model is just $150, and it has a really good review. But if you are just buying the hot air station, it is around $100. And the Kapton tape on the right side is actually for protecting other chips from heat damage. So it is supposed to be blocking some hot air blows. And the desoldering procedure looks like this. You just apply the hot air around the pins and you just take it out. It's really simple, straightforward. But if you apply too much heat, actually you can damage the chip physically and it can just burn out. And if you try to read this chip, actually you can't read anything because it's damaged. It will just return 0000 or something like that. So, and here's a demo. Demo 1. So you can see this. So just before this, actually, you saw that the temperature was 330 Celsius, around that temperature. Actually, that is the temperature actually you are using for soldering the iron. When you are using soldering irons for soldering. So I was just using same temperature for desoldering. So at that temperature, actually the solder is supposed to be melt away. So you apply the heat just around there, around the pin, and actually you put the Kapton tape around that NAND flash area so that you don't damage other parts. And the small parts actually can be blown away by the hot airs, so you can protect against that too. So I will, because we don't have enough time, I will go straight forward. So here, this part. Yeah, actually, yeah. On the right side, yeah, it's really smooth and there is no damage on other chips or other parts. It's really straightforward. And go back to the slide. And for this, so after you acquire the NAND flash memory, and you need to retrieve the firmware, and there are a lot of different methods on the internet actually. One of the methods is using some special SD reader brand, and you just connect it to the NAND flash directly, and it is supposed to read the data, but it didn't work very well. And I tried many other options, but the best option I found was using this FTDI chip. So this was introduced by Spry Mode, and he wrote a really long blog about this, and he was using the FTDI chip directly, and he put other parts himself because he's kind of hardcore. But I'm a kind of newbie, so I just bought FTDI breakup board. This one is just $20 from eBay. And there are some pins. They are doing some IOs and controls, and they have basically the breakup board is just extending the chip to have some basic functionalities. And one of the mode it is using, so actually this chip is really it supports a lot of different modes, so you can perform a lot of different operations with this one chip actually. One of the modes we are using is actually MCU host bus emulation mode. Using this mode, it's just emulating the bus from 8051 MCU. This MCU is from 1980s, and it's been on the market for a long time. So. And the commands you are sending to the chip is for reading and writing. There are some specific commands for reading and writing through this chip. And the connections between the FTDI chip and then the flash looks like this actually. So it's based on the schematic from Spry Mode actually, mostly based on the schematic from there. And I actually tweaked it a little bit, like some pins like a CE chip enable, it was not connected at first time, but it is connected with my implementation for some special operation. some data lines. So from the on the left side, it is the pins from FTDI chip. On the right side, it is the pins from the NAND flash, and they are connected together. And AD bus 0 to 7 is supposed to be sending and retrieving data, the 8-bit data. And the data control lines looks like this, and WP, CLE, ALE. CLE is for sending command, and ALE is for sending address. So you send the command, something like a read or write, and after that you send the write, which part of the memory you are trying to read or write. And there are other pins like IO or strobe lines or control lines. And they are just the basic concept from electronic engineering, I guess. And power lines, there are 4 power lines, you need to connect them. And this logic analyzer screen capture shows the basic concept very well. So if you look at the channel 2, it's sending the command first. Going up, it's sending some command at the same time. The command is going through the I/O lines. The 8 I/O lines, they are not shown here actually. And the ALE, so when it goes up, it's sending the address at the same time. And the RE, because this operation is for reading, so whenever the RE signal drops down, it signals the NAND flash that, oh, I'm ready to read something, and the NAND flash will return some data. So you are just dropping the RE signal for every byte. And these are the basic commands from the NAND flash side. And if you look up so this can be differ between every NAND flash brand actually. But these basic commands are very, very common between every brand. So for example, there are read operations. There are 3 different commands. And for reading ID, there is 90. Page programming is actually for writing data to NAND flash. And block erase, you can just erase a whole block. And so on. So according to your own NAND flash brand, maybe they can support some additional special mode. So for example, read operation, you need read 1 and read 2 functions. Read 1 is 00 and 01. And 00 will read the first half page of the data, and 01 will read next half page of the data. And read 2 will read some OOB area, out of band data, and those out of band data will be used to record some meta information about each pages. The reason why you need 2 read 1 operation is that because the internal buffer is smaller than whole page, so you need to split each read. So you can't read the whole page in one time. So read operation looks like this, but because we are out of time, I'm not going into the details, but you can find a lot of reference materials about this, how all those signals work for reading. And actually, you can verify that using logic analyzer yourself. You can just put the logic analyzer on each pins, and you can just catch the signal, and it will help you to understand the whole operations. And the interesting part is from the source code side, the software side actually. It is actually doing the same thing as whatever it is doing from the logic analyzer, the underlying side. So from here, it's sending the command from the first line, and it's waiting for ready signal. The second line is 327, and after that, it's sending the address, and it's waiting for ready signal, and actually, it's reading data. If you go to this function, actually, it's reading each byte, each pages. But the good thing is that FTDI chip itself will take care of all those like underlying I/O and strobe operations. So you don't need to take care of that. So that is one good advantage of using this FTDI chip, because there are some other attempts using Arduino to read some NAND flash memories. I guess it will be more of a hassle because they don't support these basic functionalities from FTDI chipsets. So the other equipment we need is actually TSO48 socket, and you can just mount the socket here, and this one is really convenient instead of just soldering the flash memory to breakout board. And this is the final product you get using this method. And this socket is around $20 if you order it from China, and this breakout board around $25. So under $50 you have really nice NAND flash reader and writer. So the commercial ones, maybe they have really good functionalities, right? They can read and write much, much faster, but I guess it's more than $1,000. So this one is really cheap option. And the other good thing is that I released the one open source project that actually supports a lot of different operations. It's not perfect, but it is a kind of starting point of supporting a lot of different chipsets. And the current NAND flash memory that I worked on most is from Samsung, and it supports some special mode from Samsung. And this tool works also for Windows and Linux, and it's kind of multi-platform. And for example, I just ran it from Windows, and if you pass the -I option, it will just display the basic information about the NAND flash memory, the name and the brand, Samsung brand. The chip will return some ID field, and the ID field actually represents some special brand or something. So for reading data, you can pass R option. And R and -S option actually specifies some special option for Samsung brand. I will talk about later. And there is another demo. So for this one, you just run the Python. Yeah, you will read the data. So I just quit the reading operation by pressing Ctrl+C there to open the file. So it will read just first part of the image data, the flash memory. And it looks like a really random, sorry about this, random file, but actually there are ARM instructions here. So that one is one page, 0x 200 bytes, they are one page. This is one page, and the line address, starting address 200, that one line is actually OOB data. For every 200 bytes, there is 0x10 bytes of OOB data inserted. So it's not flat image, but every pages there are OOB data. So those 3 bytes are for ECC. And the 6th byte is actually for bed block marker. And you can read past the -S option. In this case, the speed is really fast, 240K, but before -R option was like around 50K, so it's like 4 or 5 times faster. Because I'm using some special mode supported by Samsung. It supports some block read mode. So instead of reading page by page, you can read block by block. And in that case, the speed increases a lot. And you open it up, the image file again. Actually, I passed, let's go back again actually. Here, when I pass the command from here, I pass the -O option. It will just remove any OOB area so that you can acquire the flat image. You can just work on directly. So this image might be same as what you will get through JTAG. So it's all same. I will pass it faster. So this one is actually opening the image file directly from IDE, because the first part of the image file is actually ARM instructions. They are first stage bootloaders. You can actually directly disassemble it. And this is ARM architecture. And make it code, it's jumping to this address. And then those are all those instructions. They are doing some really low-level initialization. And it is really hard to understand, but still useful. So you save, I skip. And this is for writing the image file back to the NAND flash. So if you change something or patch some byte from the NAND flash, you can just write it back, and you can just put it back to the device, and you can put it up. So I guess this is for this demo. So next part, the write operation, pin state. You can go deep inside, because I'm going to release this presentation anyway. So also I presented similar stuff from Recon, and I deeply went into the details of this whole thing. But I'm going to concentrate on other stuff from this presentation actually. So this is for writing. And this is for using logic analyzer to capture how they work. So from here, actually, the software part starts. So as I said, there is a data, the page, and there is OB area, and ECC, bed blocks. And the first thing you need to consider when you are trying to reverse engineer this NAND flash image is actually ECC. ECC is, the concept was actually invented like 1950s when people are using punch card to program. So whenever you punch each card, there are a lot of chances that you make mistakes. Just one or two holes, wrong punch holes, that will make you to punch every holes again. So in that case, if you just put some checksum at the end of each punch card, then it will guarantee that the whole punch holes are correct, and above that, it can actually fix one or two small mistakes. So this actually table shows how this concept works for modern like NAND flash memories. So for this one, it is using 512 bytes of page size, and each bit actually represented as one cell here, and each P here, these blocks P8 apostrophe P8, P16, and P1 and 2 and 4, these are actually representing each hashes, the parity bits. For example, P8 apostrophe parity bits, you are using the first byte and second byte, and you are using just every even byte to calculate one parity bit. For P16, you are skipping 2 bytes, and you are using 0, 1, and skipping 2 bytes, and 4, 5, and so on. And from the Python code, it's really simple code. And you are doing it for the columns too, right? Bit 2 and 3, and skip 2 bits, and bit 6 and 7. And the code looks like this. It's really simple code, but the power of this scheme is here. So if you combine every parity bits, they can fit inside just only 3 bytes. And using these 3 bytes, for example, go back to here. If you think that, for example, bit 0 is wrong, it will trigger P8 apostrophe, P16 apostrophe, and P32 apostrophe, and so on. It will make all these parity bits wrong. And on the column side, it will make P1 apostrophe and P2 apostrophe and P4 apostrophe wrong. So by knowing which checksums are wrong, you can actually exactly pinpoint one bit actually made the checksum error. And checksum has only two states, 0 or 1. So if it is wrong, it will be the other one. So in that way, ECC can fix bit errors. So that is the basic concept. And for basic, the bad blocks, the bad block checkers actually happens for in the first and second page of each blocks. One block is usually maybe 32 pages for this NAND flash that I worked on. So for example, this one, this is the start of the block, and everything is filled with 0. And for Samsung flash memory, the 6th byte should be FF if the block is valid. So if it is 0, it means that the whole block is not usable. So here's a demo. Actually, if you check flash memories, it is really common seeing the bad blocks. Usually you see 2 or 3 blocks, two or three bad blocks, and sometimes like 4 or 5. So dash uppercase B, yeah, you see that there are 1, 2, and it is checking 3 and 4 bad blocks. It is really common. So and the other one. So actually you can dump. We are dumping the first bad block here. Dash B option will specify the block range. So we are retrieving 400 block, and we are saving it to file. Opening from the hex editor, you can see that everything is filled 0, even the OOB data from address 205 is filled with 0. So this whole block is unusable. So we skip, and you can pass that C option, it will check the ECCs. This operation is much slower because it's reading whole pages. For every page, it will read the whole pages, and it is calculating ECC for every pages. But usually you don't see ECC errors. I never seen ECC errors from the chips I worked on. So this is it. Go next. So you have some solid flat image. You can acquire some solid flat image using this method, and we are going to next step. So if you worked on, for example, a USB stick, maybe you have totally different thing. But if you worked on embedded device, usually you should have some layout, something like this. So from the block 0, the first stage bootloader will be placed, because when ARM CPU boots up, the microcode inside there will actually look for some boot devices. If it finds the NAND flash memory, it will just pass the control to the first page of first block of the NAND flash. And after that, there should be some more advanced bootloaders. Usually people use U-Boot or other open source bootloaders there. And after that, there are actual file systems, JFFS2 or YAPS or other file systems. But in this case, they were using JFFS2. And if you look further, the first stage bootloader looks like this, and it shows some very interesting strings, but it's really hard to understand unless you are familiar with ARM instruction, the architecture. And the U-Boot side, if you open up the U-Boot code, it actually shows some very interesting strings like U-Boot parameters and all these interesting stuff. But also, the vendors actually modify the U-Boot for their own use, and they put their own stuff. In this case, it's actually identifying each platform. There are different platforms like MX550 or MX570, and it is just identifying those architectures. And for the U-Boot images, these are the actually payload for U-Boot. and they have their headers, and you can just load it from IDA directly. But the IDA doesn't support multi-file image that well. So in that case, you can use my tool, -u. It will dump out the inside U-boot images, and it will save each file, each images to the files. So one of the images were RAM disk, and you can just mount it from the Linux machine. And this one is actually Linux kernel. And kernel images, you can load it from IDA. So here's the demo. 1, 2, 3, 4. Yeah, this one. So you pass the -u, small u will just search for U-boot images. And I'm passing this very fast because we are out of time here. So if you pass uppercase U, you acquire like 4 different files. So it has 2 U-boot sections, and each one, the first U-boot 00 has 2 files inside it because it's a multi-file image. And the good thing is that you can open it up from the hex editor, and there is the header. I'm passing it along. Yeah, I'm loading one of the images from IDA. I set the CPU to ARM. And it shows the disassemblies directly, so you can understand what they are doing. I'm passing along faster. So the other image is actually archived image, and you can just unzip it, and that one is actually file system. So you just open it up, it's filled with 0, but if you go down, there are much more interesting strings, some file names, something like that. And you just pass. So, and that's it for extracting. But if you copy it to Linux machine, the image you just acquired, this image, and that one is almost 8.4 megabytes. And if you use a file command, it actually shows that it is ext2 file system. And using the MTD RAM or MTD device, you can actually mount it. DD, I have all the details inside the slide, so it's just flashing it and mount it, ext2. And if you go inside to the directory, actually you can access every file there. And you can modify the file, and you can use DD to create an ext2 image, and you can flash it back to the NAND flash. And you hacked just the device. Yeah. So yeah, there are a lot of interesting stuff there, but we are skipping it. So JFFS2, the most interesting part is actually JFFS2, because the RAM disk is just containing some very, very basic binaries, but JFFS2 has a lot of interesting vendor-specific data or files, binaries there. So the good thing is that for JFFS2, the out-of-band data contains the marker for JFFS2. So it's extremely easy to identify JFFS2 file system if you have NAND flash raw image. So these specific bytes here, A519, these are used for identifying JFFS2 file system. So if you find these bytes from the first page of each block, the whole block is for JFFS2. So it's really easy to extract it, and you can do same thing as what I did for RAM disk to mount it to the Linux system. You can modify it and so on. So there is a demo, JFFS2. This is for mounting. Extraction. The tool, NumFlash tool, will support it. And Python, NumFlash, and you pass if you pass -f, and you can specify the image file you acquired previously, and this command actually found two different JFFS2 file systems. One is very small, the other one is big. And if you pass capital J, it will actually dump out that image, removing any OOB data so that you can just directly work on the file. So it just dumps out, we skip. Yeah, it takes some time. Yeah, and that's it for this one. And you can mount it from the Linux system. This one is around 61 or 2 megabytes. From here, and you are doing same thing as the RAM disk and DD, and you mount it, and you go there, and there are a lot of interesting stuff. Some the POS-related programs there, some custom programs and users and passwords. There are passwords there. Maybe you can try to crack them, or maybe some default passwords, and there are a lot of interesting stuff there. And the other stuff is the last step is actually resoldering the chip back to the machine. There can be a lot of, you need some training actually, skills for this. You maybe ruin a lot of boards, but eventually you can do this, because I could do this. Actually, I was not really a hardware guy, so let me see one. So this one. So you put the flux on the pins. First, I'm skipping it. So flux. And I was using some direct soldering. I'm not really good at this, but it's showing just one of the methods that I was used. So in there, basically you are repeating all these, and you are just removing the bridge. And it takes, for this one, it took almost 4 minutes for one side. So the other side, 4 minutes, it takes like 10 minutes. So under 10 minutes, you can just putting it back to the board, and you can just boot up the machine, and usually it works well. So the last part here, so we have only 3 minutes. So you can, maybe this one is from some commercial option. You can buy this, and if you put it to the board, actually you can mount the flash directly. But this one is really hard to solder because of this angle here. And so I come up with this, some development board. So you put this socket here and use flex cable, and you can extend it to outside, and using breakout board you can connect it to the socket, T-sub socket directly, and I suspected whether this will work. It worked fine. So you have some development board yourself under maybe $20 in this case. So I went further and put other pins here. So one side is connected to the programmer, the other side is directly connected to the NAND flash memory. So one side you program, and the other side is you just put up the device, and so on. And this one is the last part. I have only 2 minutes, but this one is a really interesting part because the tamper detection thing. So these POS devices are really popular target from the hardware hackers or underground people, because if you tamper it and somehow you can sell it to someone, or you can use it to someone, you can collect the credit card data, track 1, track 2 data using this, if you can put some Trojan horse or whatever inside it. This one, I don't know. So they are selling it from the underground market. You can see a lot of advertisement like this. And for the device that I worked on, they have some tamper detection thing. For example, the stickers there, if you unscrew it, you should tamper it. But the thing is that you can use some hair dryer, maybe. I didn't try it that much, but you can find a lot of videos doing that. So maybe you can use that method to temper it. But the other really serious temper detection is actually inside it. So the left side is front cover and the right side is the back cover. And if you look at this, there are some connection points here, 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 here. And they are supposed to be connected to each other. But how? It's through this device, this plastic device here. So if you look at it closely, so there is this rubber thingy, some plastic thingy, and there are some contact points. The really interesting thing is this, the whole outside of this plastic is actually connected through a cable. And the cable is using some kind of paint that can pass the current through. So if you try to temper it in any way, it will cut the cable. Yeah, I have only two slides. So if you try to temper it anyway, it will break the connection. So in that way, the chips inside the Verifone device will know that the cover has ever opened. So there is no way to access CPU or NAND devices directly without not cutting the current between front and back panel. And probably something is running constantly there and checking for the connections. So if you temper it and connect it back together, actually the software knows it. So you temper the device and you should clear it. But I don't know how to clear it because it's a kind of proprietary information, right? So you might need some special device or software to clear it. But the thing is that from the JFFS2 file system, there is a process called the sysmod. And if you disassemble it, and there is the source code, the disassemble code, it exactly branching, and you can just patch it somewhere here, and you can just bypass the whole thing. So the thing is that the hardware scheme is really, really genius, right? You can't put anything inside the device without breaching the hardware that like a plastic device. But the software, from the software side, you just flip one byte and you can just breach whole hardware protection, temper detection thing. So the thing is that, so this one is the last slide actually, almost last slide. So the question here is that does security by obscurity work? Because the Verifone SDK is very distributed very limitedly to those who takes their training, who identifies themselves, and the training costs like 20K or something like that. So the SDK is not public, and it's really hard to acquire the SDK. So in that way, they are control the security of the device. But if you use NAND flash thing or other technique, if you open up the files inside the file system, everything is too simple. Just change one byte, whole temper detection thing is just broken. So there is one point here, and the conclusions, you can use NAND flash memory technique to the situations where you can't use JTAG, especially for USB stick researches. I guess USB stick doesn't have any JTAG, right? So in that case, you can use this method to dump the low-level structure from USB devices. It will be really interesting how all those USB devices from the markets are working. So I'm really suspecting whether they are really removing the files when you are removing the file from your operating system. So maybe it will be a really interesting topic. And temper detection doesn't work if you are using some other method. And that is the conclusion. And credit to SpriteMod for the original design for the NAND flash reader and writer, and NAND tool from the SpriteMod and other guy, Carlos, I don't pronounce his name well. So yeah, thanks for those people. So without the information from them, I couldn't come up with other things. And that's it. So maybe we have some questions. If you have questions, you can come up to the front. Yeah, that's it. Thank you.